Hello, everyone. Can you all hear me?
I hear you.
Thank you, Eduardo. Okay, I'll wait another minute just to let everyone join, and then we'll begin. Maybe less than a minute. Okay. Just finalize one thing. Okay, we'll wait one more minute to let Aurel join, the presenter of today, because he has some internet issue. And then we're gonna start.
Hi, everyone.
Oh, here he is. Hi, Aurel. Okay, so we're gonna start. Welcome everyone to the third ZK Proof webinar. And before I'll present today's speaker, today's topic, I want to give you, as always, a bit of background about who we are and what we're doing here. So we are ZK Proof. ZK Proof is a global movement of companies, developers, practitioners, companies, individuals, everyone who are coming together in the purpose of standardizing zero-knowledge proofs. And we're doing it because we see all the potential in this technology, but we understand that in order to actually bring it to practice, we need to come together and build together standards and build together the practices that will actually make it usable in a larger scale. We're doing all kinds of things. One of the things that we're doing is a guest blog post series. So the next blog to be posted is by Professor Justin Thaler about interactive proofs. You'll be able to see this blog as well as other blogs on our website, zkproof.org. The other thing that we do is this webinar series, the reason why we're all here today, we're doing it collaboratively with the Ethereum Foundation and ZK Global. And the goal of this webinar series is to bring experts in this technology and to make them explain the fundamentals, essence of zero knowledge. And today we're hosting our third episode for this series. And we're doing all this as a lead up to our main event, which is the third ZK Proof workshop that was recently transitioned to an online workshop following all the Corona issues. But although it's online, we are planning a really, really interesting and immersive experience. So all those of you who thought of joining or already bought tickets, it's happening and it's going to be really, really cool and really interesting. It will include all of these great speakers, really the top leader, like the leading academics and researchers of cryptography. So really, there's going to be a lot to happen. And you can all join it from your home. So it's an improvement. So without further ado, I want to present today's speaker, Aurélien Nicolas, from his cryptography engineer at QEDIT. And today he's going to give us a special and very interesting session where he's going to walk us through zero knowledge and zkInterface while he's going to do live programming in front of us. So it's going to be really interesting. and I'll leave it to you, Aurel.
Thanks, Jan. So let's jump right into it. Welcome, everyone. I'm going to share desktop. All right, should see an open editor. So I will explain what's going on right now. So what you see is just whatever I was doing up to this point, right? This is, I'm just in the middle of something, so this we'll just continue from there. That's the concept of this session. But a little bit of background first. We, as part of zkproof.org, we have a proposal for a benchmarking framework. So we want to benchmark different zero-knowledge systems that are comparable together. And as part of that, so during the zkproof summit, we will discuss what should be benchmarked, what should be standardized. But the other part of this is that we have to develop tools to actually run the different zero-knowledge frameworks that we have. So we're going to do one of them. So we're going to execute one zero-knowledge tool, in particular something from LipSnark. That is going to be the first to be benchmarked. So benchmarking tool is just has just been started. It's not in a working state. That will be for the next session probably. But what we thought was that since every framework is kind of written in a different language and it's always sort of complicated to compile and to install everything and get to run. So to make it possible to run it in the same framework, we're going to use as a common interface just processes, like executable programs that run, take some input and write something on the outputs. Right? So every framework can do that. For instance, with LipSnark, right now LipSnark is a library. So we're going to write a main program that uses it and measures the runtime and take some inputs from the benchmarking tool. We've prepared the inputs, execute it, and then it will get back some result. So, and we'll be able to do that for every other framework in every language, as long as it can be a program with input outputs. So there will be more details and structured presentation about that during the zkproof summit. So about the input and outputs of this program. So the benchmark is going to be have a wide scope. So it's going to be about performing some functionality, for instance, a proof of set membership in a very generic way. But one sub-scope, more limited scope of the benchmarking is to compare zero-knowledge systems that take R1CS as input. So it takes secrets. So we say secret a lot, referring to R1CS formats. So we're going to focus on this part right now. The benchmarking framework is going to define one secret that performs set membership proof and give it to the prover, to the proving system. So this doesn't exist yet, but the format that we're going to use does exist. So we have here a proposal for a standard, which we call zkInterface. If you've attended the previous workshop, maybe you already know about this. But for those who don't, I'll just show the basic idea here. So I hope everyone can see this. Basic idea of zkInterface is that there are all the framework in zero knowledge. Those guys here, they can generate secrets. So they can be programmed. Each of them has some kind of DSL, some kind of syntax to create a secret and a bunch of gadgets to implement functionalities. Those guys here and many of us can make proofs and they can verify proofs. And zkInterface is the protocol in between them. So that any front end can be used with any backend. What we're doing now is this part, basically this arrow here. So we have lipsnark, not gadget, but lipsnark provers, because lipsnark has both, right? It has a front end code and it has also some provers. So we're going to focus on the provers. And the benchmarking framework will be one of those. It will generate the secrets to be proven. So we're doing this part. And since we don't have a benchmarking framework and we haven't even decided what the secret is going to be, we're going to use just a pre-generated file. Because this is a protocol, zkInterface, designed as an interactive thing. So you might have this guy here running as a process and is talking to the other one also running. And they communicate, that's a protocol. But we can also store the messages in a file, right, for convenience, for testing. So this is what we do now. So I generated some files. I'm going to show them in the IDE. Not here. Yeah, right here. One. So by the way, all of this you can find on GitHub. QEDIT zkInterface. So you can find everything again. And this is the repo that I'm working on in the IDE. So I generated test messages. So basically what is going on this bus here. It's a binary format, okay? So not much to see, doesn't know, it's just binary. But there is a JSON representation as well. So we can see it. So that's one example of a message that the frameworks might send to each other. And we have a few like this. And they're just hard-coded, they're not a real secret, they're just an example. So that our lipsnark prover is going to be able to read this and generate a proof about it. And later, the benchmarking framework is going to write the actual files, which will be much bigger. So that's what we have. We're actually going to use this one. So it's this much data, and we'll just go back. We'll go back to it as we read it. So again. So by the way, here we have multiple implementations. We are looking at the C++ implementation because lipsnark is a C++ library. We have some in Rust as well and some in JavaScript. So let's go back to the C++ library. We have a CMake. So that's kind of your entry point here. We have a CMake, like very basic. It depends on lipsnark. It depends on finite field library for arithmetic and GMP for arithmetic. And it's going to make an executable called bucket. So that's the executable that the framework, the benchmark is going to run. So I can execute it here. So what I have right now in my backend.cpp, I have a main one. Okay, so we're here. It doesn't do anything real right now. It's this kind of a skeleton. It's compiled, it's a program, and so the benchmarking framework is going to be able to execute it. How did I do that? Right now, I made a read file. So I have my test message hard-coded here. So that's not so great because for obvious reasons. So I want my program now to take it as an input. So we can use standard inputs. I kind of like to do those things with standard inputs and use cats, right? This is what I mean. So right now I have my backend. And what I want to do, generally people do things like this, like input file equal and something. But why do that? I have already cats. Test messages and this one. And use pipe. I hope everybody is familiar with this. So that's what I want to do. That's what I want to do now. And later I will do a benchmark, something else. Then it will be configured. Benchmark 1 year, or however we're going to call it in the future. Of course, that doesn't exist yet. So I hope that's clear. So let's try to do that as the first simple thing. Real quick. I have my so I have to read the buffer because zkInterface is it defines a binary format, so you only need to move the bytes somehow. So let's move the bytes. So here I have my path file. Okay, so probably I should be able to just replace this by stde. Something like that. No. By the way, I'm not a C++ programmer. I'm more a Rust or Go guy. So, but it's part of the fun. See how when someone tries to do that, how much trouble they might have to integrate those things together. So let's just go to Google. This is real life, right? This is getting hands dirty. What's this? Yes. Maybe not test file here, maybe. No, it's not an IF string. Is it an I string? And here, so let's make it a to-do and go back to this later. So we're going to do that. Now let's go to another step. Again, I'm not doing C++ every day, so that's why I don't know how to do this. Let's see what happens to our buffer next. Load. So I started preparing again a skeleton, a draft, and again I'm just in. This is literally where I stopped, and I'm in the middle of this. So what I'm doing here, I made a class to hold it. Oh yeah, because libsnark uses classes a lot. So the base class of libsnark is this protoboard, and you're going to create a protoboard, and then you have a lot of functionalities, and each of them is a class. So you're going to instantiate all of them. So they're called gadgets. So you instantiate them, and then you connect them through some variables, and the gadgets are going to write into this protoboard. So we're doing that. We're making a class like this, except this class doesn't know what to write into the protoboard. So if it's a fixed functionality like everything else in libsnark, they know what to write inside of the protoboard. So what part of a secret, because they're building an R1CS secret. I hope it's not too confusing for people who don't know what that is. Here, our class is special because it's taking this information from outside, from the file. So it's kind of dynamic, but from the point of view of the LipSnark protoboard, it's going to be the same. All right, so we're storing the buffer. Now, let's see how to parse it. There is, the format we're using is a flat buffer. It's a serialization format from Google. It's like a protobuf, if you want. And here, everything you see here is called into the flat buffer library, or it's auto-generated code. So let's look at it. I think it's time to go back to content of so what is the content of those files? We have here, so this is again on GitHub, a file, it's a flat buffer format. I can try it real quick. And here it tells us what structure. It's a language. It's an interface definition language. You can define a structure, so it's like struct in C, except it's called table, but that's like struct, okay, in C. And we define what fields they are. So, connection field. This one is going to be important. So that's one type of message that the benchmark can send to our LipSnark backend, and there are 3 of them. There is constraints, R1CS constraints, so that's the part of the secret, and there is witness. So the witness is the actual values that you need to prove. Again, I hope everybody is familiar, otherwise this is going to be confusing. But this is the actual secret data from the prover that are used to generate the proofs. They are going to be stored in the message witness. So we have this, and this is converted to C++ and to every other language. And we have here. So here it's a generated code. It's just an interface, a header file, which is very convenient. There is no one-time library, just a header file and some more header files here. And everything gets compiled together. There is no linking. So it's not very readable because it's auto-generated, but it basically lets us read those fields. Let's go back to the other one. Yeah, this is the homepage of Flat Buffer. So it has a tutorial, something about. Well, this is where I just take from the tutorial in C++, and I just run this. So we just copy paste these things and adapt it. In particular here, so this part of the tutorial is about writing messages, but this is already done. So right now we want to read, and the interface to read looks like this. You make a buffer of bytes. So this we have already from the file. The auto-generated thing has a bunch of get something, get type of message, and that gives you another pointer, and then you have again auto-generated members. So how does that look for us? This is an example about monsters for games. Here we don't have monsters, we have secrets and constraints, which is even worse. And so how did I do that? I create an instance of my class, give it the buffer. I don't know if it's the best way to do it, but let's just make a copy of the buffer to have it there. And later I'm going to, at some point, need this secret kind of message, a constraints type of message, and the request. Not in this order, but I'm going to need this later. So what does that do? Okay, I made this find message because there are 3 types of messages. And nice things about zkInterface is that because there are multiple ways to use it here with our benchmarking thing, we have one way to use it, but there are like it's like a protocol. So there can be multiple types of interaction, and you might need multiple messages for doing the interaction, and you can concatenate them. You can take the bytes and concatenate them. So that's very convenient because you have, then you need, because we're doing things with processes. So we have just one channel of bytes, right? And we can write multiple messages in sequence on that one channel, like std in that I was trying to do earlier. So that's going to be convenient, but we do need a little helper function. Okay, so I did that, just iterate over the messages and look for one in particular inside of a concatenation. Oh, by the way, I always click, I go inside, and then I just, when you hear me click it, I'm just coming back. So this gives us the message. This gives us an object, or it's actually, yeah, let's call it an object from the auto-generated code. So it's all very ugly, but it has methods. So we're going to be able to use it. So we are ready. We get here the messages ready to use in code. So that was something out of the way. What do we want to do next? So let's go to the end goal right now. As I started here, we want to measure time to generate a proof. So here I just use that classic begin, end, and print how much time it took. Does it still work? No. Here it breaks. Okay, let's just fix it. Real quick, we'll do that later. Oh yeah, how are we going to communicate with our benchmarking? Here I wrote it took. So the proposal in the benchmarking proposal is to make something special, some special outputs. So here I have lots of debug outputs that are useless to the benchmarking framework. So I'm going to do that. Let's call it PK proof benchmark course, or some special marker that you cannot do by mistake, and something like this. So I'm just kind of inventing this. So I propose making this. Let's say everybody writes their own like prover, and all they have to do is output a line, so they can output anything they want. They just output one line that looks like this, and the benchmark is going to parse it to find the time. Maybe let's add some fancy stuff, like some extra metadata. Iteration equals 1, and duration equals what was measured in the middle. And I think everybody can do that in every language. It's going to be very easy to communicate with the benchmarker. All right, so that's nice. What? So let's try to actually do something. Let's try to actually do something with the protoball. So here I initialize my protoball. Next, what I don't have yet, I want my gadget thing here that reads messages. I want it to take the data from the message and input it in there. And after that, okay, so let's reorganize. This is setup, generate the constraints. This is for proving. Actually, I'm going to put it inside of the measurement. So, so, where is, oh yeah, this is it, this is. So, I want my tool to generate the constraints. Somehow it's going to write it into the proto board. And then once it's done, so we have to do something here. Once it's done, I will get a constraint system for the proto board, and I will, so I started this, I will use a prover on this constraint system. So a prover makes a key pair. I'm not interested in benchmarking this, so I do it outside of the measurement. By the way, this is why there is always a lot of setup, and it's kind of difficult to, we don't want to measure the setup or the startup time. And so we could have invented something, but I think it's just simpler to you know, have the benchmarker execute the program and measure the time from start to finish, but then there's a lot of noise because of startup setup time. So I think it's easier if each tool measures in its own way, just begin and end and measure how much time, maybe make multiple iterations, and that's it. And you can do here any setup you want, even if it's slow. And this is going to be slow because it generates the prover key to generate the proof. So however long that takes, see if it actually works, probably not. So that's setup. Setup is finished. Here, oops, this. And once we have our key pair, okay, it looks like it's crashed because it's probably taking some invalid input. So see it crashed here without an error message. But after the key pair, we'll have, it goes here. Because here we'll make a proof. So the proof takes the prover key, the input, and auxiliary or private inputs, which we have to initialize here. And we're going to take this data here. So the prover will give it inputs, and the inputs has to come from the zkInterface message somehow. So this method here is going to read the message and it's going to somehow produce those things here, the input. That's the next goal. So this crashes. I don't know why, probably because it's not implemented at all. And this is the constraint system. So here we are diving into libsnark to understand how it works. Not an expert in libsnark either, by the way, just using it. So which is also the point. That, is it possible to do this without being an expert in it? We have this, and can it be somehow null or something? And here I don't have an error message, which is difficult to troubleshoot, of course.
Did you initialize the curve?
Yeah. Is someone talking?
Oh yeah, I was asking if you initialized the curve.
Oh, very good point. Very, very good point. And you happen to know by heart how to do that, right?
It's the curve name underscore init, I think.
Curve name, which is IBM probably.
Yes.
I don't think I have completion for that. So where am I going to find?
Okay, this is the function.
All right. Thanks, Kobe. So this generator here is going to use an elliptic curve, and the library has to be initialized. So probably the first time it does an operation on the curve, there is some kind of constant values that are not initialized. And without Kobe, it would have taken 3 hours to figure this out. So to do the curve, because LibSnack supports multiple curves by the way, so you also have to initialize them. You see LibSnack uses templating a lot. And here this is the shortcut. So LibSnack supports it has this abstraction over what a curve is and what a field element is, as long as it can do arithmetic, can be used. But here for our main program, we're going to use a particular one. So I made a type definition here and just all of this. Choose the curve and we get the type of fields, and we're going to use this everywhere. So we don't try to be generic anymore. Maybe later, if we want to benchmark different types of curves, then we'll have to do everything like this, right? Everything templated like this. All right, we have to do my run, take a template. But for now, we just make life easy with a hard-coded one. So after we have to figure this out, it will no longer crash. So let's try to actually populate our constraint system. So how does that work? I'm asking myself, by the way. So we're going back now. The goal is to read the constraints files. Let's go back and look what there is inside of a constraints message. This thing, there is constraints, there is a constraints field, and it uses this type, so it's an array of this. And you can open this in the same window. All right, so let's iterate. Being constraints. So I have my get constraint here that gets me this object, and inside I have constraints. This is so now constraints. Oh, thank God for auto. I don't want to look at it. Constraints is an array of these guys, and we are printing right now how many they are, which is 3, and we iterate over them. So that thing is a special flat buffer kind of vector. It's not a standard vector. And the objects kind of like these things, they are just pointers. They are pointers inside of the buffer of bytes. So they don't take any memory of their own. So this horrible kind of typing thing, it's all to say that it's a pointer to the buffer that's interpreted in a special way such that the methods are going to read the correct data every time I call a method like this. So for instance, the size method just knows at which byte to read to get the number of elements inside of the buffer all the way back to here from the file. And so without copying, without allocating memory. So if you are careful, if you spend the time, you can make this extremely efficient with zero overhead. Right? And then everything is inline and it's like a very efficient program. If you want to use it for millions of constraints or billions, you can do that very efficiently. with some effort, of course, but it's possible. So we are iterating over the constraints and print something, and that thing was working. Constraints on variables. But it's not over. So let's say we have here. So this is an iterator of one constraint. So it's like one constraint. So it has linear combination A. So it's one of these guys, variables. The variables, it's an, how to explain that? The constraints in R1CS, they are like, it's like an inner product, or you have one vector of variables with coefficients. So in zkInterface, we refer to variables by uint64. So it's a unique identifier. So in the entire system, the entire process, it's a unique variable ID. And inside of our constraints is going to be an array of these IDs here, and values are interpreted as coefficients. So when you iterate over those variable IDs, so you know which variable to take, multiply it by the coefficient in the other array, and that makes the inner product, that makes the constraints. And the sum has to be 0. I mean, in R1CS, so it has to be, no, it doesn't have to be 0. It's, so let's go all the way. R1CS constraints, it's like A times B minus C equals 0. One of those variables thing. So here we have the ABC, and each of them is an array of variables. So I can write the A. Here is going to be some variable. Let's say it's a variable number 2 times the coefficient of 1 plus something, plus a variable 4, whatever it is, multiplied by 3. So that's the A. And that's one of these objects, variables. So here we have variable ID number 2, coefficient 1, ID 4, coefficient 3. And that's stored in there. And that is here in my code. So here with this loop, I'm iterating over the content of this A. Again, I'm sorry if you're not familiar with R1CS, it's going to be very confusing. And here again, the B has a number of variables and filters. And same for the C. So LibSnark must have a way to, it has a different way of doing that, right? So we need the variables, and we need to do, let's initialize it somehow. What is this? Let's pass it as a parameter. That's one way to do this. Oh no, yeah, normally in LibSnark, you don't have to do that, but here we don't. So let's, next step. We stack, so we look for an example from LibSnark. And we look at an example gadget. So this is an example program from the LibSnark library. It has also a protoboard and variables. That's what we're missing. The PB variable and PB variable array. So we're gonna need those guys. We're going to need to allocate. So we have to detect all the variables that we need, make some kind of loop, and allocate. So we're going to do that later. Then it has a gadget. And so this thing, oh yeah, it does pass it as a parameter. So we have a gadget for the inner product. Well, just a random gadget from LibSnark. And this is similar to what we're trying to do. So it's going to be a good example. We're doing something that's effectively a gadget. Actually, I'm going to call it a gadget. So it's a zkInterface importer gadget. By the way, feel free to interrupt me if you want to go in a particular direction or if you have questions, or just let me know. I mean, we're not going to get any any job done right now in an hour. Just let me know what you want to talk about. In the meantime, I'm going to look how do they do it in Lipsnack. So we have some Lipsnack authors on the call, I believe, at least Eran, maybe others. And we are looking how they did it, and they did give it like this. So that's how they access it. Photo board, so I'm just going to do the same. Oh, and it then goes, it uses itself another gadget. Oh, because there is a gadget common class, probably some kind of abstract class. And this one just does it. Gadget. And it takes the protocol by reference and it's going to write inside of it. So I believe the syntax for that is this. Maybe not. Again, not doing C++. Let's not do C++ things. Let's do simple things. Like this. This should work as well. Let's do Java. I don't recommend doing it this way. Is that possible? Constructor is explicitly initialized. Oh, so you actually cannot do with Java style in C++. No, you know. It's kind of... Okay, I don't remember. How do I do it? Classical Java. So this we have. Library with field is not the same, right? This one is a template, maybe this one is just hard coded. And what am I missing? Class gadget. Constructor. Oh, that's no way. We'll do that later for the syntax. Well, someone will let me know what's the syntax. Anyway, we have our reference to the protocol, and we wanted to iterate over the constraints, and we want now curly braces. And now we have our protocol. Yeah, I can go back to this, and it's going to be something like that. My reference, just like this. And I will end up here. To do it will remind me. And dot. And we are making very slowly a little bit of progress because I can get constraint system, and I'm sure this thing has a add constraint. Yeah, it has an add constraint. So how are we going to call this? Because we have to make the difference now between protoboard constraints and zk constraints. So we could call here, we're going to make a zkInterface constraint, and it's like this. And we want to somehow convert it. So this type of thing. This. and I want to call it constraint. That's it, and somehow initialize it. Later on, how do I initialize this? I don't know if there is another form of documentation for LipSnark that I'm missing, or maybe this is it. Form. Okay, so that's what I explained earlier. And how do we create it? We have to make, of course, a linear combination, ABC. So again, we'll have our zk somehow we'll have our zkInterface A, and we'll have LipSnark, or it's called PB for LipSnark things. I'm going to call it PB because every time I'm going to have two types of objects with the same name, right? The protoboard thing and the zkInterface thing. So let's call it LC for linear combination A. And I'm just going to do that 3 times. Like this, and like this. And those things have to be typed like this. So we are learning how to use the library at the same time, right? On the fly by reading the code. That's what we're doing right now. So these constraints, and once I will have iterating the constraints. No, so here, this is not the right place, not inside of this loop. This loop here is going to write things inside of my linear combination at some point, but not now. I need this and reformat. This is the best thing ever. Reformat, and it just takes everything. Thanks for nothing auto completion. Are we good? Yeah, we're good. Except those things are empty. So now our job is to go read the zkInterface stuff and write inside of those guys. And then just add it. So how do we do it? Linear combination. What does it? What can it do? What can it do? So it takes a variable. Let's try. So here it takes a variable without coefficient, and probably there's another one that must probably take, or probably it has some kind of multiply. Yeah, it has a multiply operator. So what I can do is get a variable, create it empty, and then add terms. I'm going to create an empty one just like I did, and later I'm going to iterate over my stuff and call add. Can I make them one by one? Yeah, of course I can make them one by one. So probably there's going to be some kind, instead of doing that, I'm going to make a function that converts the zkInterface linear combination to LipSnark linear combination. Let's do it inline first and then extract it as a function. So we go back to our fat buffer definition. Okay, but I said I can add something, but what can I add? What can I add to it? Add term. Well, this looks perfect. Variable and coefficient. Let's do variable, and I assume the coefficient by default is 1. Let's make the assumption. And of course, we're going to do the code to verify this, and this is 1. First, the button is not support field. But how do I get a variable? So that's the big problem. This is going to be the big problem in our little project here, is going to be how to get the variables. Because we have to discover them first. So let's assume we understand here how to do this. Right, we do add term variable. Here, as I'm iterating, I'm getting an ID. So this is a var ID. We said it was a uint 64. And it's just like taking it like this. This is what I'm really doing. So much better now. And here I want to do find a PB variable based on this variable ID. It's going to be PB var. Cool. So of course we have to make sure to even this somehow. This thing we already know the type, it's variable. And acceleration by reference, which is nice. Okay, obviously. So we'll figure out how to find it later. Probably protobot or something. Like find by ID, I'm sure, or must be an array. One of them must be an array, and you can just index into it. So this assumes that our indexing in zkInterface is going to be the same as the protobot. But so we're going to do exactly that. So by variable IDs, they are numbers, and by convention, the number 0 is like unity on a field. So it's like number 1 as ID number 0, and then there are inputs. So 1, 2, 3, 4 can be inputs, and then there are like private variables. So we're going to follow the same convention, and hopefully we can use exactly the same variable ID. So it's just going to be an index. Variable ID is going to be an index inside of my protoboard, and my protoboard, I can show you, has definitely a list of variables somewhere, or in constant system maybe. Someone has a list of variables. Number of variables. No, wrong bit. Oh. Oh, it must be this one. Variable. And I know that there is this val here, which is used to set value. Okay, but let's not dive into this right now. So we know what we will do. Figure this out, figure out how to do this later. Oh, now let's just make an empty one, and maybe it's still complex here. No, of course not. But I'm not interested in that right now. What are we going to do? Oh, so to find the variables, so the constraints, they can refer to any variables in any order. I just say the ID of the variable. So the variable is going to have to exist before. And that's a strange problem that we're going to have, because in libsnark, normally they are prepared, I believe, by the caller, the main program. It allocates variables. If it needs 10 variables, it allocates an array of 10 variables and pass it to the gadget, who definitely knows it is getting an array of 10 variables. But here it depends on the content of the file. So we'll have to read into the file to find out how many variables we need and allocate them, and to kind of do it the other way. So here I'm going to do iz.find out how many variables. actually unallocate them. Or here it's how many. And then I'm going to do for loop of how many and do pb.allocate or something like that. Or maybe it doesn't allocate array. Okay, going for something like this. Let's do this. Let's do this first. So I like to have names, strange names, and then later, you know, I just rename them with the ID. So I always do what I always do. A second pass of renaming things before committing and pushing. So this information, how many variables we're going to need? This is going to be written in V5. Where is it? Of course, I close it. Of course, it's V1 number directory. So we have to go back to these types. So there is a secret. Okay, this is how we're going to know that. This free variable ID is how these systems communicate with each other, how many variables they need. Because there is a common space of variables going from 0 to infinity, contiguous, or maybe not necessarily, but by convention they are contiguous, and they have to know which one to use. And so it's going to happen that the benchmarking tool is going to generate this very big secret that needs lots of constraints. Let's say it needs 1 million constraints. It's going to generate this file and this message and put 1 million in this variable. So this is going to be how many variables are needed before that. So when I receive, I'm here, I receive a message like that. With this number, it means all these variables before that, they are used. And I can use new ones in different contexts, but right now I'm not generating any secrets. So just need to know how many they are. So I get into secrets. I already made a helper to find this secret message. So I can use it, get secret, and secret. So this entire thing is a pointer, like cast in a very strange way, and you should have this. So this is the generated method. And that's it. And that was easy. Once you know how to look. And let's always use the correct type. But it's next. So next, someone has to allocate, or maybe this method could do it. I don't know. Maybe it will be easier to do this, like allocate. Allocate, and basically it's going to do this instead. And this guy is going to call allocate. What does IZ stand for again? Importer gadget. So let's rename this importer. Okay, by the way, it's been an hour now. I don't know if you guys have any question at all.
Anyone with questions? This is a really good opportunity if you didn't understand anything.
I'm jumping left and right just to show all the moving pieces that have to come together.
By the way,
Just a way to
questions
discover
will
the
also
library.
be around. I just said that if anybody's interested in collaborating or implementing any part of the zkInterface, feel free to share it now or contact Aurel or myself later. We're happy to have collaboration around zkInterface.
Yeah, I have no idea if I lost everybody or not. Or maybe not. I don't know. Daniel, what do you think? Do you have any question, Daniel?
Maybe if you could give kind of a few tips, just kind of speaking of what are the important aspects to pay attention to when using zkInterface or implementing anything using zkInterface, and then I think we could maybe close it up, or if anybody else has other questions.
Yeah, another thing we need to do is actually the coefficient here. So find the variable, and next here it will be find the coefficient, convert the coefficient. There is a helper for that. There is already a helper, which is in our castle. All right here. So we also have to convert. So Lipsnark is using its own type of fields. And here I have already written the helpers to convert from the bytes in the zkInterface message to the correct field type. So I already have that, so I'm just going to call it once I figure out how to access my variables here. Right here. So that's one thing to do. About the structure. I didn't talk about witness generator. So once I figure out my constraint, I'm going to do something similar about the witness. So here, when I have the witness, so I have specific values that the benchmarking tool is telling us each variable should get. So we're going to do the same here. Iterate over each variables. And then we have our protoboard, and we're going to assign values. I believe this is late. Is it? Oh, it's a weird, I think it's a weird C++ thing where you can assign like this. Should be that. Maybe. Because it's written as one. Oh, here is the array that I was looking for. So protobird has these values, and basically, so in the protobird, it starts empty when we allocate, and then we just read from the message and write into it. So again, we'll have to convert. So find the value. And the value is in the witness. I think I have a helper here. Auto ID and auto values. And I have a helper, I don't remember the name, but it converts somehow. Then I get the ID, and it's going to be ID equals iterator. So that's variable ID, right? the ID equals values. Well, actually, I'm just going to iterate just good old way. And this works like you expect. How does it? Calling a private constructor. Oops. I think it's object. Yeah. So that's all. So every time we have to configure to find the right way to convert. Yes, I'm going to print this at first just to see that we're doing something proper. And here, finally, we write the value in the protoball. So we're going to do that. The right conversion here. And the backend is going to, okay, it does the key pair once. So here it's going to do it every time because it's just a fake key pair, but it does it once and then later generates a witness. So our protoboard gets full of values, which means that when we call a prover like this, which is provided by libsnark, no, this is not how it works. That means afterwards we'll have to do this type, but this function expects. So there will be another step of conversion. Maybe I can do it right away. So what I want is a R1CS variable assignment. Oh yeah, but the reason I'm using the protoboard in the first place, so I could do without. I could generate that thing because I want to use the prover, and the prover only needs the values, which is just an array of values. And I could generate that without a protoboard. The reason I'm doing it with the protoboard is that later I want also to reuse this code. I want to reuse my gadget for other cases. So here I'm using it as just one gadget, which is the entire input from the benchmarker. And that's one protoboard, and then we make the proof. But later, and this is actually how it started, we want the user to be able to, they have a project or something they want to prove, and so they start a protoboard and put all their gadgets and all their variables and start expressing what they want to prove. And as part of it, they can use the zkInterface gadget, or even several times. Right? And it's going to just play nice and add the constraints alongside your other constraints and so on. So that's why I'm doing this, because there is a bigger end goal. But if I just want to do my benchmark, I could do this much simpler. Yeah. So I guess I can stop here, or just go where, if someone has any question, I can go that way.
Anyone have any specific requests that they would like to look at on the zkInterface side? And by the way, if anybody has any feedback, we would greatly appreciate it, either now or later as well.
Well, I am wondering about how to tests would work for sonic constraints. It's not R1CS constraint. It's very similar. But
yeah. You can convert it. So this is ongoing, just figuring out lipsnark, but there is another one that works. Not this one. Okay, I don't have it checked out. But there is another one which is written in Rust that works. So probably I would refer to when I'm going to continue this work on lipsnark. I'm also going to check back on my Rust version, but I have, for instance, this one. So this is the same concept, but in Rust. And this is for bulletproof, and bulletproof has the same kind of structure as Sonic, I believe, if I'm not mistaken. It's very similar, but it does take R1CS, and then I do a conversion. So you're going to recognize, so there's the same kind of concept where we have messages. I'm showing the screen now. Yeah. Bunch of conversions, so every type of object is being converted. And then there is an extra step right here, which is figure out how to do the arithmetic secrets for bulletproof from R1CS. So you have to do a kind of phase of allocating multiplication gates and later adding the linear constraints. So there are multiple ways to do that. I did a straightforward way that is relatively easy to understand, I believe, but there are ways to optimize in some cases how to do that. But it's possible, right? They are very similar, arithmetic secrets and R1CS, so you can convert them. And this zkInterface adapter here for bulletproof, it does it. So for Sonic, you want to look into this. You want to look into this and do something similar for using the Sonic API.
Okay, thank you.
And we also intend to expand the scope of zkInterface to support also arithmetic secrets, and as it's becoming more and more in demand, for instance, for Sonic, we might support it right away in zkInterface. To be discussed at the workshop, right? So if you attend the workshop, please try to talk to us or attend the session, and we can discuss that kind of things.
Okay, yeah, I will attend. Very nice, cool,
yeah.
Cool work.
Okay, anyone, any more questions to Aurel? Okay, so Aurel, thank you so much for the great session. I know it's not easy speaking in front of your own screen for 1 hour, so you did very well. Everyone else, this code is on GitHub, so you can access most of it on your own time and go over it. And if you have more questions, to post it on the community forum. And I will also send all of you a feedback form to hear more about your thoughts about this session, and maybe if you have ideas, what do you want to see in the next sessions, that will be great. Other than that, have a great rest of the day. Stay healthy, stay safe, stay happy. Bye-bye.
And see you in London or remotely.
Remotely, yeah.
Remotely, yeah.
Talk to you there.
Thank you, everyone.
Thanks, everyone. Goodbye.
Bye.